Hi guys. So if you remember in the last video, the introduction to the Laplace transform, we said that the Laplace transform takes a function. So let's call this x as a function of time, and is able to do something kind of fantastic because it turns it to, no longer a function of this t stands for time. Can we call this? Let's call it the complex domain. I can call this the frequency domain. Alright, so you can call it the complex domain, the frequency domain. They have the same implications. So the Laplace transform is this tool right here in the middle, that's able to take a function of time. Alright, let's say like voltage as a function of time, current as a function of time, and transform it into a different function which doesn't depend on time anymore, but is now a complex function. Is a complex variable. It's now in the complex domain, the frequency domain. What does that mean? This S that you're seeing here, alright, let me write that here. S is a complex variable, meaning represented by sigma plus JW. I sort of went into this in the first video, but let me see if I can go a bit more in depth. So in sigma plus JW, S is complex. And what this does is that it does two things for us. This JW, right? I mean, recall this is all going to be in the exponent of E. So this JW is going to be our oscillatory, our periodic part. It's a periodic part of our function, and this is our, I don't know how it's called, but let's call it something like growth. Okay, like our growth factor, because if sigma is greater than 0, then you have a growing function. If it's less than 0, you have a decaying function. So this is what makes sense when we throw this into the formula. So in the first video, we actually didn't do any mathematics, but now this is the first time we're going to mention what happens in the Fourier transform. Okay, so the Fourier transform looks, though these arrows look cool. Yeah. Okay, so what is the Fourier transform? Hey, did I say Fourier? Pardon me. So what's the Laplace transform? Sorry, I meant Laplace if I said Fourier any other time. So the Laplace transform of a function, you denote it by big L. Okay, so let's say you have f of t. Okay, the Laplace of this is going to be capital F of s. Let's just get that out of the way. So f of s, okay, is the Laplace. It's like a cursive L. Is the Laplace of f of t. Actually, it's the same type of practice. It's the Laplace of f of t, and that is the integral from 0 to infinity of f of t multiplied by e to the minus st dt. That is exactly, let me make this a bit clearer. So L of f of t e to the negative st dt, just so we can always look at this someplace. So what does this mean? F of t is our function. Okay, what we start with, voltage as a function of time, current as a function of time. That's going into our integral. E to the negative st is what's going to help us map from our time domain to our frequency domain. So the mathematics we're doing here that usually involve, dv dt or di dt, okay, these complex differential equations are all going to map into simple algebra, which is, multiplying by s squared, 1 over s cubed, etc. So differentiation turns to multiplication by s. Integration maps directly to dividing by s. That's exactly what the Laplace transform does. So e to the negative st, okay, so let's put this complex number. Alright, so e to the negative st is going to be e to the minus, how do you write sigma? Sigma plus jw, all multiplied by t. So if you apply the indices, the exponent rule, that's going to be e to the negative sigma t multiplied by e to the negative j omega t. Alright, are we cool? I really hope we're following. This j omega t is the Euler expression for sinusoids, for cosine, for sine. Or if you want to express periodic functions as sine omega or cos omega, Okay, if you want to express this exponentially, this is how it's going to be expressed. So we know that this part of the complex number s is for the periodic nature of it. All right, our functions are going to be periodic, and this is for, look at this, is e to a negative integer multiplied by time. So this is a decaying exponential. All right, so we know, oh, our functions don't oscillate forever; they are decaying over time. That's exactly what happens with the Laplace transform. So it just takes a function f of t, then maps it from time, so it no longer has to deal with time, straight into the s domain, the complex domain, the frequency domain. All right, I believe I've said that before. So our limits, all right, we're going from 0 to infinity. What does that mean? We're dealing with casual functions here, meaning we're only concerned, the Laplace transform is only concerned with once the excitation is applied to your element. Okay, once the excitation is applied to your element, so that means we have no concern for, negative infinity all the time, far backwards into the future. We only want to know, at t equals 0, what happens, and how does this map out? What's the limit of this as it starts from 0 and tends to infinity? Okay, so that is the breakdown of the Laplace integral. You take a function f of t, which depends on time, and then the Laplace transform is this big scary box, Laplace, that makes it a big function of s. Where in f of t you deal with integrals, you deal with differentiations, and here you just deal with simple algebra. So when you take your function f of t and then you move it to the complex domain, okay, I think I can do a really cool diagram. So when you take your function f of t and then you move it to the complex domain, to the complex plane, the tool that does that is the Laplace transform. Okay, Laplace, there's an L here, it's Laplace transform. So here you do with derivatives and integrals. Here you deal with simple algebra. So you solve. Now you have capital F of s, right? You have small f of t. Here you have capital F of s. So you solve with algebra in f of s, and when you take the inverse Laplace transform. Okay, so the inverse Laplace back into the regular plane, and then you get your final answer for the solution. All right, we're going to be definitely go more in depth in later videos, but for now, to get comfortable, let's get a proof of action. Let's actually do a Laplace transform of a function. See what that looks like. So let's say that f of t, our function of time, f of t is e to the minus 18 u of t. This is the unit. U of t is the unit function. Okay, it's an indicator of, all right, this is coming on at t equals 0. Really doesn't play a significant role in your calculation. So this is our function. All right, e to the negative 80 u of t. What are we going to do? We're looking for the Laplace of this. That's going to be capital F of s, right? And then going to be the Laplace. How do you draw? I think it's curly brackets, but I usually use a sort of square brackets. It's going to be the Laplace of, remember our function, Laplace of f of t. Okay? Which is the Laplace of, and this is really elaborate, which is Laplace of e to the negative 80 e of t. Alright? So now we recall the integral. Let me write that out so don't forget. Capital F of s is going to be the integral from 0 to infinity of e to the minus st times f of t dt. I'm gonna put this in a box so we don't forget. All right. So that's this, and that's going to be our integral from 0 to infinity e to the minus 80 multiplied by e to the minus. We're going to discard the step function, the unit step function, once we enter the Laplace, times e to the negative st dt. Things are about to get really interesting. So what do we have? We're going to use our law of indices. All right, we have a common base here. e and e are common bases here, which means we can add our exponents. So let's get to work, okay? So that's the integral. Let me write, okay, that's the integral from 0 to infinity of e to the minus at minus st dt. This is absolutely correct. Okay, we're going to factor out the minus sign. So that's the integral from 0 to infinity of e to the minus. This is going to be summed together now. A plus s, t comes out, dt. So now we can evaluate this integral as simply and straightforward as possible. Okay, we're going from 0 to infinity. The integral of the integral of e to the negative kt. You're going to differentiate the exponent and divide it and take the reciprocal of that. Let me explain what I mean. If you're integrating e to the minus kt, okay, differentiating this exponent is going to give you minus k. All right, so this is going to give you 1 over minus k, then whatever's inside your integral e to the negative kt. As simple as that. So that's exactly what we're going to do to evaluate this simple integral. Differentiating this, we're going to get, don't be deceived though, this is still a constant. So that's going to give us negative 1 over a plus s. Okay, it's going to be 1 over minus a plus s, so there's nothing else in bringing the minus sign up. Then multiplied by e to the minus a plus s, all multiplied by t. Okay, and now we're going to take our limits from 0 to infinity. We can solve since we're taking to infinity, you usually put a number here. All right, they can call this n and take the limit of n tends to infinity. That's how you solve it. All right, but let's move on regardless. It's still taking the same conceptual steps. What are we going to do now? If you recall how we use limits after an integration, this is going to substitute into the function. Then you're going to subtract that from when you substitute the lower bound. So this is the upper bound. Let's call this UB. Infinity is the upper bound, and 0 is the lower bound. Let's call that LB. So we're going to substitute infinity into the expression, then subtract that from the lower bound, UB. So let's get straight to work. Minus 1 over a plus s e to the minus infinity, actually, because we're going to do minus a plus t times infinity. So e to the negative infinity. All right, cool. This is 1. Then subtract that from minus 1. That's a really long minus sign. Minus 1 over a plus s e to the minus 0. Okay, because you have minus a plus s. This is a constant. Like, these are constant terms. Then 0 into here is going to give you minus 0. So e to the negative 0. Okay, what is happening here? You have a constant raised to negative infinity. So that is going to tend to 0. The limit of this is going to tend to 0 over time, because this is essentially 1 over e to the infinity. 1 over a very giant number is a very small number. So this entire thing is going to clear to 0. And our entire expression, so capital F of s is going to equal this. We have e to the negative 0, the same as e to the 0. And any constant raised to 0 is going to be 1. I see what I'm saying. So let's substitute this. So that's going to be minus times minus 1 over a plus s times 1. It's coming together now. Substituting this, that's going to be simply 1 over, s plus a. Simple and short. If we were to bring this out, then this is, we've done it. We've done the Laplace transform. So the Laplace transform of e to the negative at u of t is going to be simply 1 over s plus a. And that is all there is to it. As simple as that. You take the integral multiplied by e to the negative st, and you evaluate it from 0 to infinity. And we've been able to do that. As you go on and you get into higher calculations, you won't always have to derive every Laplace transform from scratch. We have what we call Laplace tables. Okay, so we look at Laplace tables. They tell us for so and so use case, this is the so and so transform. So they help with the forward and the inverse Laplace transform. But this is the only question we're going to do today. It's just to understand the nature of the integral, what each of the terms mean. So as we go on, in the next video, we are definitely going to get more in depth and solve a lot more questions on this.